looking at equations of lines in two-dimensional and three-dimensional space, and we've been working with points and creating vectors. So the vectors that we've been creating have been specifically direction vectors, where we were either showing the x and the y component for two-dimensional shape or the x, y, and z component. But now we want to take it one step further and actually write a vector equation. So you need to know what the components are. The a value here would be a point, a fixed point on the line, and the b value would be specifically the direction vector of the line. So think of an equation of a line. You have slope and a y-intercept. Now we have a point and the direction of the line. The t is kept there as our variable, where it can be any real number. So here is a breakdown of what the vector equation will look like. We have what it's equivalent to. And then we have the x and the y at the point that it goes through, the t, that's our variable, and b1, b2 is the direction vector. So you can think of b1, b2 as the slope, as we've done in previous sections. Remember, slope is rise over run. So the b2 is in the numerator, the b1 is in the denominator, which looks flip-flopped when we write it as a direction vector. So let's put this information to work. We have a point, 1, 5, that's our x and our y value. And then we have our direction vector, which is the x component and the y component. So we're going to start just with writing a vector equation, and then we'll move on to the other two. So we're going to start by putting x and y, and we put our point, which is 1, 5, plus t, that's our variable, and our direction. We always have to state that t is an element of real numbers. And that is our vector equation. Just like what we've seen before, if we wanted to, we could set up two equations by following the horizontal and putting that together as an equation and the vertical. When we actually separate them into the horizontal and vertical components, we can actually call those parametric equations. I'm just going to highlight those so you can see them separately. And so we have x is equal to 1 plus 3t. We also want to state that t is an element of reals. It's the same t value. And y is equal to 5 plus 2t. And t is an element of reals. What's good about these equations when they're written in parametric form is that we can find the point that corresponds exactly with one t value just by subbing it in and then finding the x and finding the y. Now taking the parametric equations, and then we can actually find the equation of a line. So that would be our Cartesian equation. So think of our Cartesian plane, which is just a regular xy plane. And what we do is we take our parametric equation, so we take the parametric, and we solve for t, and then we equate the t values. So I would take x, I'd subtract 1, and I divide by 3, which gives me t from the first equation. And then I take y, subtract 5, and divide by 2, which will give me t. Now, the t has to be the same, so we can put those equal to each other. Then we can cross multiply. Oops. 2, so we get 2x minus 2 is equal to 3y minus 15. Rearrange that. I'll just put it in standard form. There is my equation of a line. So in the second question, it looks like we are given two different equations. So we have our parametric form. And it's saying find the initial position of p, knowing that p has our x and y component, which are both relative to t. So the initial position means that t would have to be equal to 0. So if we're going to find the horizontal component, so x is 0, and 2 minus 3 times 0, which gives us 2. And we also have to do the same for the y. So 2 times 0 plus 4, which is equal to 4. So that means that when t is equal to 0, the x value is 2 and the y value is 4. So that is actually a point on the line. The reason it's a point on the line, remember, is because we can take those parametric equations and rearrange them for t and set them equal to each other to find the actual Cartesian equation. Illustrate the motion showing where t is equal to 0, 1, 2, and 3. So we have to go step by step to find each one. So in the interest of time, I just went ahead and found those. So I have the points, 2, 4 that you're starting with here, and negative 1, 6, negative 4, 8, and negative 7, 10. So I'm going to go ahead and plot those. So here I have that plotted. I started with 2, 4, and going this way. Now I'm going to have a closed circle at 2, 4 because that's when t was equal to 0. And then I can continue the arrow because time is continuing. So this is t is equal to 1, t is equal to 2, and t is equal to 3. Remember, that is seconds. And then it says find the speed of p. So if we're going to find the speed of p, for every second you can see that the horizontal component is negative 3 and the vertical component is 2. So horizontal is negative 3, vertical is 2. So if we want to find basically the hypotenuse, we take that and make it a little bit bigger. We can say that this is negative 3 squared plus 2 squared, which is 13. And we're told that this is meters per second. That's how we find our speed of the particle. Now let's do the whole thing over again, but in three-dimensional space. So we have our vector equation, which is our point, a1, a2, a3, plus t, and remember t is a real number, and then b1, b2, b3 is our direction vector, and we can then change those to be our parametric equations, again, just by putting the horizontal, vertical, and the z components together, the three-dimensional components. And then we can do an actual example. So for this example, we have the point. So we can set this up as 1, negative 2, and 3 plus t, and then our direction vector. So that's 4, 5, and -6, where t is an element of real. So that's our vector equation. And then to find the parametric, then we just take the components together. So x is equal to 1 plus 4t, y is equal to -2 plus 5t, and z is equal to 3 minus 6t, where t is an element of real for all of them. For the next question, we're asked to come up with the parametric equation, and instead of giving us a point and the direction vector, they're just giving us 2 points. But if we actually find vector AB, well, that's giving us the direction vector. So then we can do -1 minus 2, 0 minus -1, 2 minus 4, which simplifies to be -3, 1, and -2. So this is our direction vector. And then we can use either point. So it doesn't make a difference. So we can set up x, y, and z. I'll just use the first point. 2, -1, 4 plus t. And then our direction vector. This t is an element of the reals. And it's asking us to put together the parametric equation. So why don't you guys try that, and then you can double check with mine. And there is the answer. We can also find our angle between the vectors. The formula is the same. The only difference here is that notice it says acute angle, which we've been asking about. We always want to find that acute angle, so we'll take the absolute value of the dot product. So we really need to look at what is the information that's given. So they're giving us the parametric equations, which, if it helps, you can even write these as vector equations, so -3 and 1. And the reason I changed this would be L1. The reason I changed these to vector equations is because we really need to look at the direction vector. And remember, the direction vector comes from the part that it's being multiplied by the t. So do you need to put them back into the vector equation? You don't, as long as you know that the direction vector is coming from the part that's multiplied with the t. So our equation is cosine theta of b1 dot b2 over the magnitude of b1 and the magnitude of b2. So you might be asking, what are the b's? Those are the direction vectors. Same notation from earlier. So we have -3 times 2 plus 1 times 3, absolute value, over the magnitude. So we have -3 squared plus 1 squared, and 2 squared plus 3 squared, which gives us -3 over root 10 times root 13. So 3 over root 10 times root 13 cosine theta. So theta is equal to 74.7 degrees. And in this last question, again, it's asking us to find the angle between them, except for it's giving us the direction vectors already. And I see that these are identical. So if they're identical, then they're parallel. So if we have two vectors that are parallel, what is the angle between them? Well, so we're saying that B1 is equal to B2, so therefore the angle between them is 0 degrees.